person to join through Facebook. It's live on Facebook as well.
YouTube.
As we all know, this afternoon, we are looking at having our CPD, the first CPD in this session, and it's on the topic GNSS data processing and results analysis. This is happening because we have some few people helping us or some companies helping us in doing this. In the course of the time, I will give their names and then we will appreciate them for helping us out. So we are going to have two presenters this afternoon. We are going to have Reverend Professor John Ayer. I think that is somebody that needs no introduction, but for the benefit of the following protocol, I will introduce him as somebody who, a professor who has been with us all this while, and he works, or he's a lecturer at the Kwame Nkrumah University of Science and Technology in the Department of Geomagnetic Engineering. And he's also a reverend. So we are in good hands. He's somebody, for the last time that I counted, he has about 30 or so papers to his credit. And so I think it's still counting. So we are privileged to have somebody who really understands the subject and has worked over the years through the same in this area. The other person that we are expecting is to come on board. He is coming on board from the, let's say, the machine vendors and the programmers and the people who provide those machines for us to use. He's coming in the name of Hexagon. As we all know, Hexagon, PDS Hexagon. I think that is Leica. And he's no meaner person than Sovia or my brother Derek Chinibua Menu. He will do his presentation right after Professor Aye, and right after we have taken some, how do you call it, some questions for Professor Aye. Like I mentioned earlier, the companies that are accepted to help us through this are PDSA, who are partners of Hexagon. We also have DSEC. We have Sevcon Engineering, and then we have 360 Survey and Engineering Limited. So without much ado, I think we are already 10, 20 minutes behind time. So I will leave the floor for Reverend Professor John Ayer to kick the ball rolling. Thank you.
All right, thank you very much. And I hope that you can all hear me because I'm coming all the way from Kumasi this time. And I will spend the first 20 minutes of this CPD to do a brief introduction, and then Derek would come in with a practical processing of some of the things that we'll be talking about. And so the topic, as I have been given, is GNSS data processing and results analysis. And of course, we cannot talk of data processing without doing a brief on the data gathering. So let me, on this first slide, give an introduction to Global Navigation Satellite Systems, or GNSS. And as we all know, it refers to satellite systems that provide positioning globally. And how we use it is that we have receivers on the ground which use signals from satellites to compute their positions through trilateration or otherwise. And we are talking of satellite systems such as the GPS system, or what we call the Global Positioning System, developed by the Americans. And then we have GLONASS, developed by the Russians. And then we have the European satellites, also known as Galileo, and then the Chinese ones known as Beidou. And now there are receivers that can actually receive signals from all these segments, and hence the shift from simply using GPS to GNSS. Well, GNSS have three main components. We have what we call the space segment, that is talking about the satellites that are orbiting the Earth. And with our receiver, we need a minimum of 4 satellites so that we can have a fixed solution of our location. And what these satellites do is that they send their location signals, which may be received by our receivers on Earth. And then we also have a control segment, which are ground stations, which monitor and manage the satellite systems by sending them data for controlling and calibrating themselves, their own positions. And when we are going to use it, we can say that our typical example of a station we can use on the ground to control errors is when we use a base station on Earth, which will normally set on a fixed position. And this base station on the ground, we can actually replace now with our various core stations. And then we can now talk of the user segment, which is the receivers that individual end users will carry on the ground. So the question is, how do the satellites themselves know their position? They determine their positional information using a combination of precise timing and clocks and regular updates from the ground control stations, and then also using some kind of orbital mechanics calculation. So the satellites themselves are equipped with onboard atomic clocks to provide accurate timing necessary for determining their positions. And then data is also broadcasted from the ground to them. And this data will include their position in orbit at any time. And this data is calculated using the satellite's own orbital parameters, and then it is regularly updated. So that is one of the purposes also of the ground control stations, which continuously track the satellites and update their orbital parameters, and then send these updates to the satellites so that they will ensure that the information that the satellites themselves are broadcasting to ground receiving stations are as much as possible accurate. So the ground control stations communicate with the satellites using telemetry and adjust their positions to ensure that they remain in their correct orbits. Now, what kind of data are we receiving from the satellites? The satellites will be sending us what we call zero-range data. That represents the distance between the GNSS satellite and a receiver. It will not send the distance directly, but when we receive a signal, it also sends the time at which that signal has been sent. And so when we receive it, we can calculate the time difference between when the signal has been sent and when it is received. And that can be used in computing then the distance of the satellite from the receiver position. And that is what we call a pseudo-range data. And of course, the information that is sent would often also include corrections for satellite probe errors. Then we can also have what we call the carrier phase data, where the receiver is able to measure the phase of the carrier wave of the GNSS signal. And that is used so that we can have higher accuracy as compared to only the zero range measurement. And of course, we can also measure the change in frequency of the signal due to the relative motion between the satellite and the receiver, and that can also be used in calculating receiver velocities, and so on. So in all, we are going to be receiving all this information from the satellites, their position information, and then precise ephemeris data. But we have to know that this information would be passing through the ionosphere and the troposphere to get to us. And so, of course, the data providers will also have to provide information on the ionospheric conditions which affect the GNSS signals. And this can be used to correct what we call ionospheric delays in the signal propagation, and also the tropospheric conditions, which will also impact on the signals. So we are just talking about the fact that the signal is going to pass through outer atmosphere, and then it will pass through the Earth's own atmosphere before getting to the receivers. And so we have to do corrections due to this. Then there is also what we call multipath data. That includes information about signal reflections, which can cause multipath errors. And if we have that information, then it can be used in mitigating multipath effects on our measurements. And so the raw GNSS data that we will receive would include all these different data sets, which we call the observational data, which will be collected by the receivers. And then, of course, we can use this raw data for post-processing so that we can improve on accuracy and also reliability. And usually, to be able to correct for most of the errors, we will devise different methods of collecting the data by using, for example, what we call differential methods, so that we can get corrections which would be used in correcting our data. Now, the data can also be put in an interchange form, which is known as a Gnss format. And the Gnss there stands for Receiver Independent Exchange Format. So that if we are going to use a different set of equipment, but process it, then we can have this interchange format that will enable us to not only use the proprietary software provided by a particular vendor, but any other software that is available. So understanding and utilizing these data types is essential so that we can get a very accurate results at the end of the day. Of course, we have mentioned that the equipment we use on the field are the receivers and antennas also, so that with the antennas, we can actually transmit and receive also corrections. Now, what are the methods available for gathering the data? We have what we call the static GNSS survey method, and that involves collecting data at a stationary point over a prolonged period of time. And this method is mostly suitable when we want to establish controls. For example, the procedure involves setting up the receiver on a fixed point and then recording data continuously for at least 30 minutes to several hours, and then post-processing the corrected data using software so that we can achieve high accuracy results. But in normal use, we may not necessarily spend 30 minutes at a station because we may not be looking forward to establishing controls, high accuracy geodetic controls, for example. And so we can resort to kinematic GNSS surveying, and that involves moving the receiver from place to place. And so that can provide then real-time position updates and it's mostly suitable for dynamic applications. And the procedure involves setting up a base station again at a known location. Then we now have a receiver which can now move along the survey path so that we can be receiving corrections from the base station in real time, which can then be used to be correcting the rover positioning. And that is kinematic method. And it's just similar to the differential GNSS method, which usually we recommend for most words because it will enhance the accuracy of our positioning. That also uses a reference station or a base station, and we can have again the corrections transmitted, or else we wait and then we do a post-processing where we put in the correct coordinates of the rover stage, the base station, and then the corrections will then be applied to the rover receivers. And that will then improve positional accuracy. A similar method is to do what we call a real-time kinematic GNSS processing. The only difference here is that the corrections are transmitted in real time, even though, again, we are using a base station, but we need also to have transmitters and receivers that can be receiving the corrections from the base. And when we go far away from the base, we still need perhaps to be using a radio station or cellular networks or even the internet to access these corrections. Okay. Now also we can do this on a very large scale. Hence we can talk of a network real kinematic method when we are using several base stations in a network and the corrections are again applied throughout the network. Okay, most of us would collect our data and would do post-processing. That means that we do not process until we have finished collecting the raw data. But the other method that I also want to mention, which usually is also used for establishing controls, is what we call precise point positioning. And that also, we will have to receive data or with a receiver at a station over 30 minutes or more. And there are many service providers that we can upload the data to, and they will use global positions which are known to correct our data for us and to process it and send the results to us. And so what do we have to look at before processing our data? I call it a pre-processing of GNSS data, and that will involve several procedures to enable us clean the data, correct and prepare the raw data for further analysis or applications. And I believe this is a point that most of us leave out in processing the data. When Derek comes in, he would actually tell us how some of these things can be done. We first have to do what is known as data cleaning. That means identifying and removing noise data points by doing a kind of filtering out so that those data that are have high noise levels or obvious errors will be removed before processing can continue. That will ensure that there is some consistency and integrity and that outliers which are caused by multipath effects or signal blockages are removed. And this process will also check for missing data and handle gaps in the data. Now, most GNSS data processing software have some tools for doing that. One of such is called a total electron quality control tool in many of the systems, or TEC in many of the systems for doing that. Then also we have to look at the clock correction or satellite ephemeris correction, and that involves applying corrections to account for satellite orbit and clock errors. That also will improve the satellite position and timing using precise ephemeris and clock data, which is provided by GNSS service providers. And these corrections will apply to the raw data before it can be further processed. Again, many of the GNSS data processing softwares have a tool in there for doing that. They have RTK library tools and Gamut and GlobeK tools inside the software for accounting for some of these errors. And also when it comes to the ionospheric and tropospheric corrections also, many of the providers, again, have some models inside. One of the popular models is called the Sasto-Moinen model, which can account for tropospheric delays in the data. And the softwares, many of processing softwares, again, have some built-in atmospheric correction tools for correcting for the ionospheric and tropospheric errors. And then, of course, also the big one is the multipath mitigation. One of the things we have to do is to make sure that we are not setting our receivers close to smooth surfaces and high tall buildings, which can cause multiple reflections of the signals before reaching our receiver. When we avoid multipath, it will ensure the integrity of the measurements. Again, there are multipath mitigation algorithms and filters in many of the GNSS processing softwares that can help us in doing this. And I guess that Derek will be taking us through some of these corrections in the course of demonstrating the processing using the Leica processing software later on. The other thing is to make sure that the data we are getting is in the correct coordinate frame. And here again, even though the GNSS itself would have done all its computations in the WGS84 ellipsoid, there are built-in functions that can actually project to specific coordinate systems, so that we'll make sure that our data is converted to the correct format before we can use it. So there are coordinate transformation tools in some of the softwares which can do this correction, this transformation also for us. Of course, without doing any transformation at all that it means is that the coordinate that would have been given would be far from what the base coordinate itself would have been given. And for that matter, the correction error which have to be transmitted would be very large, and some systems then put a limit that if it is so far away, then the solution cannot actually continue. So it is important to get something very close to the base station coordinates before most of the corrections also, before most of the processing can continue. And so we can apply all these corrections as differential corrections in the processing software. Okay. There is also another type of error, which is called cycle slip. And again, here again, there are tools in the GNSS processing software which enable it to determine cycle slip and then correct it before the processing using algorithms which are inbuilt. Okay. The last thing I want to talk about here is what I call synchronization, because usually or at times you would have collected different GNSS data using different receivers, for example, and you want to process all of them together. Again, you want to be able to align all of them to the time that they were collected so that they can connect to the base data. And the softwares will use synchronization tools that also include timestamps that talk of the time you collect the data which have been recorded, and also the time that the particular core station or base station you are using has also collected the same data, so it can synchronize before processing. So when we use the appropriate software tools and methodologies for this pre-processing, then it would enhance the overall quality and usability of our GNSS data. So we can have different processing techniques. We have what we call a single point positioning technique. Derek will go through those ones. Basically, it means that I'm only using one receiver, no reference, but I should be able to get coordinates. Then I'm doing single point positioning. Then we have differential GNSS positioning, and that means we set a base, and then we have rovers, and of course, the base helps us to transmit corrections to correct the rover position, whether in a real-time mode or in post-process mode. So we also, I mentioned precise positioning, which I said we will then have to observe the data over a long period of time, and we can send it to one of the processing centers to process for us. Okay, so what are some of the softwares available for processing? There are several of them, but most common ones are what we'll call the Trimble Business Center, which I believe many of our colleagues have been using. Then we also have the Leica Infinity, which Derek will be demonstrating for us. And then we have TopCon Magnet also. But there are also open source softwares like the RTK library, the GNSS SDR. They are all available. And the key features of all this is that they allow us to be able to import data and export our output, and also provide processing options for us. And usually they also have visualization tools so that you can have a display and check how the results are fitting in before sending it out or before printing it out. Okay. So then with all this in mind, it means that when we have taken into consideration most of our pre-processing tasks, and then we now do the processing itself, we now have results which we can analyze. So the analysis of the results involve ensuring that, number one, in collecting the data itself, we have had a clear view of the sky to minimize signal obstructions, which can be caused by buildings, trees, or other structures. Number two, we have spent sufficient time because the duration of observation affects the accuracy of the positioning results. I think that usually for most of our work, we are using dual frequency receivers and observational times of, let's say 10 to 20 minutes on a station. Well, of course, we would ask the regulators to actually put out a determined time duration so that we can all adhere to it. It doesn't matter how fast we want to do our work. The fact is that longer observation times will always lead to more accurate results because it will increase the number of satellite observations and also increase the ability to average out errors. So the regulator might, in the course of performing his duty, tell us that I want you to observe 10 minutes when you are doing a dual frequency receiver, or I want you to observe 20 minutes when you are using a single frequency observer for maximum accuracy. Okay. Then the third thing is the data processing itself. And of course, we have mentioned some of the errors that we have to take care of. And many of these errors can really be eliminated when we are using differential processing. And so no wonder they have told us that we should all be doing differential processing most of the time. Okay. So what kind of quality assessment can we do again? Let me talk of the coordinates themselves. We can check our coordinate output by comparing the result we are getting with known coordinates already, okay? Then one other quality assessment we can do is to use a parameter called the dilution of precision, or DOP. The fact is, when you have low DOP values, it indicates also that we have better geometric strength of the satellite configuration. Therefore, our results are bound to be more accurate than when we have high DOP values. And then, of course, the number of satellites. We have said that you need a minimum of 4, but the more the number of satellites, the better the improvement in accuracy. And then one other parameter also we can be looking at is what is known as the signal to noise ratio. The better the SNR ratio, the better the accuracy also. And of course, our final whatever is to look at the statistical analysis. And one of the ways we can analyze statistically the result is to use the standard deviation or the root mean square error. Well, I separated these two because they don't always mean the same thing. For example, if I have a very large number of points, then I can be talking of the standard deviation because that is for a population. but for limited number of points, we will be talking of the root mean square error. Then, of course, we can also be talking of the confidence intervals within, if I take a number of points, like 100 points, how many of them lie within my set criteria and how many are outside? If 95 out of 100, then I can say that I am 95% that my work is very accurate. And so usually we'll talk of a confidence interval of 95%. Of course, that can be increased also if we want higher accuracies. And I have mentioned positional accuracy, which we can effect by comparing our derived coordinates with known reference point coordinates. And of course, this comparison will help us to determine absolute accuracy of our GNSS result, and also help us to be able to identify if there are any systematic errors in the results. On that note, I hope that I have taken us through the theoretical parts, including what we have to do prior to processing, and if there are any questions, we can discuss those. Otherwise, then we will let Derek come in and demonstrate the processing using real data and using the Leica processing software. And I want to thank you for taking time to listen to me. So questions?
Question time, please. If you have any question, please, you put up your hand. Those on the Zoom, you put up your hand and we can see you and then allow you to have your question.
And then
those on Facebook.
Yeah, YouTube.
Yeah, those on YouTube. Yeah.
And then I'll relate it to the moderator for the presenters to respond. Thank you.
Okay, so the floor is open now. Right. You have a question?
Yeah.
Come.
Okay, thank you very much, Reverend Dr. Aye, for the wonderful presentation. I have a question with regards to the PPP. Currently, I have an instrument. I was able to experiment the PPP, and then what I realized was that I was getting an error of, let's say, 3 to 4 feet. I don't know what could be, what will amount that 3 to 4 feet difference when I was able to observe on a control at the survey school. Thank you.
Okay. Can I come in, or we will allow Alice also to ask her question?
Okay, then let's allow Alice to go on. Alice, please unmute and speak.
Good afternoon, sir.
Good afternoon.
So my question is, in case I'm working in an area, there is no known control around that area for me to transfer to site, and I've established a temporal benchmark over there, which I observed for a long period, then I process it. How accurate is that coordinate for me to use? Thank you.
Okay. Any other, or I can respond to the two now.
Yes, Prof.
Please there's one in the chat as well, Prof. So you can
There's
look
one
in the
again.
chat. Yes, there's a question in the chat as well.
Okay, in the chat, okay. Yeah. The chat says, is it possible to use the GNSS to get ground heights, that's autometric heights, and how? Very well. So here we have three questions. The first one is talking about the 3 to 4 feet difference. The 3 to 4 feet difference could be coming basically from how it was projected into our local system. That is what I suspect it will be coming from. But we wouldn't leave out the fact that 3 to 4 feet also could be the result of the non-homogeneity of our own coordinate systems themselves. I mean that our coordinates which we use themselves also exhibit those kinds of differences already from one place to another. And so now I don't know whether to fix the 3 to 4 feet as coming from your projection to the local system, or we have to use we have to attribute it to the fact that that is a kind of distortion in the coordinate itself you were trying to compare it with. I don't know if you understand what I'm trying to say. Hello, I don't know who asked that particular 3 to 4 feet question.
Yes, please, I understand, Prof.
And so that is prompting a chief examiner that so far as we have not yet adjusted and replaced all our coordinates with what I will call adjusted coordinates. Perhaps chief examiner will have to restrict us to using some course which they have tried and tested, so that all our work can be in harmony. Otherwise, these small differences will always come up. That's all I can say about this particular one now. The second question is talking about when I have observed in an area where there are no controls, and I've done the observation for 30 minutes to 1 hour, and I have sent the results, and it has been processed for me using ephemeris and other data that are globally available. Is it good for me to then rely on it? I think you will have to submit that one to the chief examiner, because at the end of the day, he is going to be checking the results to accept or not accept. So once he has accepted, then it can become part of his database and can be used later on also. Because according to the process you are describing, you have used a method which is usually suitable for establishing geodetic controls. So over to Mr. Chief Examiner for that kind of assessment. The other thing is talking about whether the GNSS can give photometric heights directly. And the answer is the heights that it will give you straight away are ellipsoidal heights. But if you have what we call a geoid model, which is the difference between the ellipsoid and the geoid in the area, then you can convert that one into an photometric height. What I know some system does is this. It sets a base on a benchmark, which is a pillar also that have known height, so that it can also find the difference between the photometric height and the ellipsoidal height which the GPS is given, and include that in the correction information that it is using or sending for processing rovers that are close by. For a very small vicinity, that is possible because it is assuming that as long as you haven't gone very far away, the geoid ellipsoid difference have not changed substantially. But there have to be a caution there as to how far away you can go for this to be used, for example. And so that is also a matter of further investigation. So I hope that Alice is clear about that also. The other question is, what is the acceptable baseline distance from a reference for single frequency observation and for dual frequency observation? There have been several works done on it, but I don't want to put a cap on it without having a discussion with the regulators on this particular aspect of the acceptable baseline. Because, for example, Mr. Mohammed have done some work, and he has used base distances of even 250 kilometers and have gotten some quite pretty well results. But if you put a limit on these things, sometimes it is prone to abuse by people who always will want an easy way out. Remember, even in talking about observational times, I have left it for the examiner to tell us based on several works what he thinks can be the best time of observation. And that also goes with the baseline. So I'll beg that we will defer this to a discussion with the examiner based on several works that have been done so that it can be included in the guidelines that he will give to us. Then there is another question here. It says, how different is the use of data from core stations and GPS data from receivers mounted on known national pillars in processing a cadastral survey? I think that we have tried to address that in a way. The cores are replacing the base station that you are going to mount the receiver on. So in that case, instead of having two receivers and keeping one on the base, you can just have one and you go to the field and use it as a rover. Then you will get the base data from the core. And then that is one aspect of it. The other aspect of it is that with the core and the processing and the adjustments that have gone into it, you can be sure that there is more homogeneity than using the single position points, which actually some pillars have their problems. So it will depend on which one you have used as a base and the amount of error it is introducing and knowing to you in the work. And so that is why I would advocate that when the core system is properly developed, then the examiner might limit us to the using of cores instead of every one of us using different types of pillars on the ground. I think I have answered all the questions that have been asked so far, unless there is another one that I haven't seen yet. Okay, somebody is asking, what is the acceptable ellipsoid, Clark 1880 or War Office? Good. This question, interesting as it stands, is good if we were thinking of single position processing, for example, then it is very, very relevant. But you see, because the examiner says we should use differential processing, then it sort of mitigates the effect of the ellipsoid differences. But in reality, the ellipsoid that we use for our mapping in Ghana is not the Clark 1880, but it is the War Office ellipsoid. And so that is the acceptable one. Of course, the Clark 1880 also have been provided, and so people use it, but I caution that there is a difference between the coordinates which will be based on Clark 1880 and those based on the War Office ellipsoid. And the positional difference in them is about 3 to 4 meters in the northern and about 2 meters or so also in the east. It works out to approximately a vectorial distance of 25 feet difference. And so we have to be aware of that one. Usually when you are doing some small scale work, you wouldn't even see these differences. For example, if I have a plan or a map at 1 in 50,000, a difference of that much, 25 feet, which is just about 5 meters or 6 meters, is not going to be noticeable. But when you are doing large scale, it really matters which ellipsoid you would use. And the standard ellipsoid that we are using so far, which we haven't changed yet, is the Ghana ellipsoid, which is also called the War Office ellipsoid. In many of the softwares, it will be called the Accra Ghana datum. Okay. I think somebody said his question have not been answered. Let's see which question that was. Caleb's question, where is it?
I think is the if I observe a point for 4 hours, 4 to 5
yes.
hours, and process, yeah.
I think I have answered that question. I said, yes, the person have used the correct method of determining controls by observing for 4 hours and sending it for PPP processing. But the acceptability of it will require that he submits that one to the chief examiner. So I think I have answered it in a way by saying that, yes, the coordinates are okay as far as process is concerned, but there is something he must do to get it accepted, which is to submit it to the chief examiner for his comment. I hope that is clear now.
That's clear.
Mm-hmm. Okay,
Any
so
more
if there is
questions?
any more question, otherwise we would allow Derek to take us through the processing.
Yes. One last question.
Yes, sir.
Okay, Prof, once again, thank you very much. Prof, should in
Yes, sir.
case you want to do a height work, I mean an
Yes.
engineering work around, let's say, Adan,
Yes.
how are you going to carry out that work? Are you going to assume height, or let's say you want to depict the height with reference to our mean sea level? How are you going to do that?
Very well. The purpose of the work has already determined how you will determine that. You said it's just an engineering work in Adan. They are interested in knowing height differences, not necessarily absolute height. Therefore,
Prof,
a local assumed height, yes.
Yeah, so Prof, here I'm talking about an absolute height.
Absolute height means you have to actually tie it to a benchmark, which is with respect to the mean sea level.
So in this case, roughly, how are you going to do that?
Okay. In this case, I have also mentioned something like, unfortunately, we don't have an acceptable joint model yet for the country, because you could get the ellipsoidal height, and if there is a joint model, you can convert that to absolute height for the place. That is the autometric height for the place. So if there were a proper acceptable Ghana joint model, then you can actually take just the ellipsoidal height and convert that one to the absolute height in the area, and then you will use it. So yes, it's possible by looking, there is a joint calculator online, but that gives you a model which is developed based on a global gravity kind of thing, without the small refinement in regions. So it will give you something close, but it will not give you the absolute value. That is the problem we have. So if you are still interested in absolute height, then I am afraid that you will still have to tie it to a benchmark, which is already in Ghana's high system.
Okay. Okay. Thank you so much, Professor.
Yes,
I think that this is a whole semester course that you have given in just some few minutes. Thank you so much. I think that you will be on standby in case there is anything whilst Derek delivers his side.
Yeah,
yes.
right.
So I want to bring to the attention of everybody that this event is proudly sponsored by PDSA of Hexagon, a part of Hexagon. We have a Selfcon Engineering Consult, 360 Survey and Engineering Limited, and then we have DSEC, which is Juvegio. Juvegio. I always forget it. Is it Juvegio? Yes. Juvegio, yes. That is a PP at the TVS company. Then, so I want to personally give thanks to Surveyor Maxwell Ansa of PDSA, then Surveyor past president of Utavia of Doveggio, then Surveyor Brown of Selfcon Engineering, and then Surveyor Cyril Kadebeku of 360 Engineering. So, Derek, the floor is open for you. Let's hear you. Thank you.
Thank you very much. Please, can you confirm if you can see my screen?
Oh, it's blank. I'm not seeing it.
Okay, hold on.
The sharing has started, so wait a minute, it should come.
Okay.
Yes, we can see a screen with a software.
Okay. Good afternoon, everyone. My name is Derek. I'm technical support as well as reality capture specialist for PDSA, part of Hexagon. So before I begin, I just want to give a brief introduction about the software you are seeing on your screen, which is the Leica Infinity. So Leica Infinity is a processing software to bridge the gap between the field and the office. So it is not a software only for GNSS raw data processing. It's as well a software you could use to process a TPS data. You could import your surfaces, do your volume calculation. You can actually do survey adjustments, as well as also process scanning data. But for our presentation, or for the presentation today, the main focus would be on the GNSS processing. So Leica Infinity has 4 key principles. Our principles are: we visualize the data, we prepare, we confirm, we report, and we archive. So those are the principles. So after this presentation, if you don't have any take, just remember these key principles about Leica Infinity. To visualize your data, to prepare, to confirm, to report, and to archive. So with Leica Infinity, you could see when you open it for the first time, this is your home page. Okay, we have the ribbons, as you can see up here. You have your ribbons. Okay, so these are the various models that I talked about. So we have the processing, that's the GNSS processing tab. We have the surface, we have point cloud and imaging, we have infrastructure, we have adjustments. Going back to the home page, we have what we call the information toolbar, where you can have access to the various settings of the Leica Infinity software. So when you open the software for the first time, what we do is to create your project. So if you want to create a project, you go to new project, then you can create your project. Okay. You could see that it allows you to put a lot of information pertaining which project you are doing, who you are doing it for, and actually certain details in terms of coordinate system and how you want the data to be presented to you. Either you want the local or the WGS84. The next tab is actually where you manage your data. So any project you create, you have a list of the project here, which you can manage. If you go to tools, then you are diving more into where you can select which coordinate system, which antenna type. Target type is for TPS, which I won't speak more on that. I'll speak more on the coordinate system. So depending on which coordinate system you want to use, you see from my screen now, I have a list of a lot of coordinate system currently displaying now, right? So if you are doing a project and you want to process the data, you specify which coordinate system you want to use. So there's a list of coordinate system here, which you can choose from, right? Normally, when you open it for the first time, you don't have this list. We have predefined coordinate system actually saved in Leica Infinity. So if you go to the help and support, we have various tutorials. So if you've not used the software before, we have tutorials where you can actually download sample data, and with outline documents, it will show you what to do with processing. Right? There are also videos that you can navigate to actually better understand how to process the data or how to work with the data in Leica Infinity. Okay. So to proceed, I've already created a sample GNSS raw data project, which I would want to take us through. So if I want to open the project, I just double click. And if I see that my title bar is showing the name of the project, that it means I'm in the project. So what I do is I just go to home to now work with my data, right? So in the home page, we have the navigation tab, we have the source type, the view, and inspector. Okay, so navigation tab shows you the various data that you have in your workflow. So if you have points, you have lines, you have images, all of them will be shown in the navigation tab. Data source is the folder at which the data is stored, so the source directory. The view gives you a map view of how your data is represented on site, right? So if you pick your data, you have a map view to see how the data is represented. Then the inspector is where you do the editing and the processing, selecting which one is the reference and which one is the rover point. Okay, so for this example, you could see that I have some points here. So since in the beginning I said Leica Infinity is used for other processing, right? So which one, the one that you are using is the one that you have to select. So in this example, I'm going to select the GNSS because that is the sample data I'm working with right now. So if I choose GNSS, now I see my point with the occupation time, the start time, end time, duration, and even the satellite systems that you use, and also the occupation mode, right? So from this next screen, you could see that I could clearly see that the longest time is actually my base and the shortest ones are my rovers. You could have certain data set where you have multiple base stations. So you just have to know which one is your base and which one is your rover points, right? So for this example, this point is actually my base. So in order to process, you could see that the point rows are all navigation points. Okay, so none of them is a control point now. So in order to specify which is a control, if I click on the point which is a control, you could see I have a property tab, which is on my right side of the screen. This shows you a little bit more information about the data, which antenna that was used, the point row in terms of being a navigation point or a control point. You have a local point as well as the WG884. You only see a local point if you have if you are using a specific coordinate system. If you are just using the WG884, then you wouldn't see the local point. You could see clearly from this example that I have a droidal separation. So from the questions that asks, in order to determine the autometric height, you need a droidal model. But this droidal model is actually the global one, which is not the region one. So it's more like relative, not absolute. Okay, so that is with the coordinate system that I'm using. So in order to process, we need to specify that this point is actually a control point. So if I click on this small icon here, you could see it's saying I should assign this point as a control point. So if I click on that, now the icon changes from being a navigation point to a control point. So to process, it's pretty simple. You go to the processing tab, right? You hit your control point and you say you want to make that as your reference. In Reverend Dr. Ayer's presentation, he talked about single point processing. So single point processing is actually a standalone GNSS practice, also known as SPP. And it's a method where there are no error correction made, right? So this uses the satellite to provide you with the best satellite or best location available. So if you are using SPP, it means you don't have any base station. So your coordinate is actually the position that the satellite is actually giving you. So in Leica Infinity, you can as well do single point processing in the software. So moving forward, I'll select this point as being the reference. Okay, so if I select that, you could see the color will now change from being a gray color to a red color, telling me that, okay, this point is my reference. Okay, this point is actually the navigated coordinate or the navigated point directly from the satellite, controlled from the satellite. So I would have the corrected coordinates saved somewhere. So you could see from here, there's a small pencil just by the local point. So if you want to edit this particular point, you click on the pencil, then you can now put in the correct coordinate of this particular point. So I'll quickly put in the coordinates of the point. Okay. So it's just a matter of either typing the coordinate, or if you have it in a notepad, or if you have it somewhere, you just copy and paste. Okay, since I know the coordinate that the GPS gave me was the ellipsoidal height, that is what I know on the field, I will apply this option and now edit the ellipsoidal height, because in this example, I'm interested in its autometric height. That is not what I measured on site. So what I measured on site was the ellipsoidal height. So that is what I will edit if I know the ellipsoidal height of the control. So I'll quickly click on the pencil for the WG884 position and now type in the correct ellipsoidal height, okay, and apply. Okay. So when that is done, we now select the other point and make it rover point. But mind you, if you are interested in having a correct elevation, then you have to make sure you measure your height of equipment. Okay. So to measure the height of equipment is from the pin of the control to the face center of the equipment. So you put in the correct height for each of the setup if you are really interested in getting a correct elevation. So I'll quickly do that as well. So if you have it on your notepad, or if you have it in a book, you can quickly update the height of the equipment. Okay. Okay. Okay, so when that is done, you make sure you've entered your correct height for all the points. Okay, I think some of them didn't appear. Let me just enter the height. Okay. Okay, so okay, so you could see that from the antenna height, we have something we call a carrier offset. So normally when you are measuring the height of equipment, we would have to measure from the pin of the control to the phase center of the equipment. The phase center of the equipment is normally inside. So inside the equipment where we can't actually see with our eyes. So Leica has this measuring tool which has already calculated that phase center and has added a certain offset to that particular measurement. So what you do is that you just measure the height of equipment and it adds up the antenna height with the carrier offset and gives you the true height of equipment. So with that particular carrier offset, we have two types. We have the short and the long. So with Leica equipment, if you're using Leica equipment and you're using the Leica measuring tool, if you are using the short one, the offset is normally 0.245. If you are using the long one, it's 0.36. So with this example, we use a 0.36 offset. So it's normally from the pin to the carrier face of the equipment, which is the L1 and the L2, which we are not able to see with our eyes. So that has already been compensated within the measuring app or the measuring tape for you. So you just measure the height of the equipment. Okay. So I'll add the 0.36 to all the setups. So that is going to give me my true height of instrument. Okay, so when that is done, you can go ahead and process your data. But before you process your data, you can glance through to see the quality of the data that you picked. Okay, so for example, the base data, you could see with the various satellite systems, these are the quality of data that I picked. Normally, we don't want to see a lot of white lines that shows gaps between the data. So it's a way of kind of like visually inspecting the data to see whether your data is actually good or not, right? So to go ahead with the processing, you just click on process. And the software will actually process the data. Okay, so you could see from here, we have our station coming from the control point, and these are the individual points. Okay, to dive into a bit of the reporting of the data, to the reporting, you see a graph that shows you which satellite system that it tracked. We have the SV positions, which shows you the elevation as well as the azimuth. Okay, so it's just a sky plot of the various satellite systems, right? At which angle that the GPS was actually communicating with the base, or sorry, with the satellite, the azimuth as well as the sky plot. So at which various angle that it was communicating with the satellite. If I go ahead to the statistics, right, you could see the various frequencies that of the satellite system that it was tracking. So for the GPS, you could see it track the L1, B1, and the E1. If you look at the ambiguity, you could see most of the positions were resolved. So meaning the data we were picking were actually not under a canopy. The sky was really clear. So most of the ambiguity were resolved. Okay. So Reverend Ayer talked about the DOP. So DOP is an indicator of the geometrical strength of the satellite being tracked at the time of measurement. So what it simply means is that the effect of the satellite geometry on the accuracy of the GPS. So it quantifies how well the satellite or how well distributed the satellites were. So we don't want very high, so a low DOP means we were actually, we will have good results, right? So you could see from the graph, there were certain times that we had very high DOPs, but if you are taking the optimum or the mean the mean deviation of the DOP, you could see we had a very good distribution throughout the data capture. So to export your results, you can actually print out a detailed report of the processing I just did. So that gives you a bit more detailed on the baseline, the satellites it used, the coordinate system, the various satellite systems that it tracked. Okay. So if you look at this reporting, it gives you a very detailed representation of data capture that was done on the field. So it gives you the coordinate system that you use, the various parameters in terms of which sampling rate satellite systems that was selected, which solution type, the models in terms of ionospheric and tropospheric models. Okay, you could see from the next line the baselines. So this report is kind of like a detailed report on the processing that we just did in terms of the standard deviation of the controls, in terms of the L1 and the L2 satellite systems, right? If you are looking at a bit of the satellites that it tracked, you have a graph and a signal representation of how the satellite tracked. As I said in the beginning, we wouldn't want our data to have a lot of gaps. So like this, if you have a lot of gaps in your data, then processing, having a fixed position becomes a problem. Yeah. So this is more of the azimuth, as I showed earlier, the angle at which each satellite system was positioned whilst the GPS was actually receiving signals from the satellite. You have the DOP, and you have the observation statistics. So where which the number of L1 that was used, which ones were rejected, the number of satellite that was tracked, which one had a fixed position, which one didn't have a fixed position. It gives you more of the epoch as well, percentage of the epoch in terms of the fixed and non-fixed. So the idea is that we want our non-fixed to be minimal. We want our fixed position or the fixed percentage to be of the highest, right? So if there's if you process your data and you see that there's a high level or a high percentage of the non-fixed, right? You can drill down to the positions or the specific satellite that couldn't, we didn't have enough data or correct data from, then you can actually exclude them from the processing. So to do that, if you go to the data, if you go to the satellite use, if I choose manual, I can specify which satellite system or which satellite I should use. So if you realize one of the satellites was giving you bad data, you can actually take that off from your processing. Okay. So this is kind of like a detailed report. So as I showed with the satellite that was rejected, you could see at what time that it was rejected with no data. So with this, you have a thorough representation or a thorough data or a thorough reporting on whatever you've processed in terms of the GNSS data that you picked on site. Okay, so this is actually done for each of the rover points. So each rover point gives you that particular detailed reporting. So you could see the first one was with the first rover point. If you move further down, then we are now looking at the second raw data point, right? We as well have a simple reporting which puts all the data together as one. So if you don't want a detailed report, we have a summary reporting as well, where it gives you a summary of the satellite that was tracked, the DOP, which ones were rejected, which ones were used. So that one is more like a summary of all the rover data. So it gives you a summary of the data representation. Okay. Okay. So when you're done with the data processing, we then store to say we are certified with the data or with the result that we have. So if you come to our map view, you could see now you have a green or a sign baseline showing that the data is well processed. Right? You could see from the beginning when the data wasn't processed, it was gray. Right? So now you could see that the data is well processed, showing the fixed position. Okay. Showing the fixed position or fixed coordinate of each of the points. If you click on any of the points, you could see the residuals, the position quality. So you could see the position quality for the eastern, northern, as well as the photometric height. So you can actually observe for all of them just to see the position quality for all of them. So that is with the GNSS processing. I want us to just dive into how data representation of the RTK data is also displayed in Leica Infinity. So with RTK data, your corrections and everything is actually being broadcast in the field. So you have a correct data, which is actually processed with points or position quality being at the minimal, right? So there are instances where you've done your RTK data and you've made a mistake, maybe with the control, that is the control data, which is where you have your base station set up. Leica Infinity is a powerful software that you wouldn't need to actually go back to the field to actually process your data. So you could see from here, I have my base point here, which shows that all the points which I picked were referenced to this particular position from the screen, as you can see. So assuming if I made a mistake with, let's say, a specific, let's say the height of instrument. I made a mistake with the height of instrument. Leica Infinity is so powerful enough that you can edit the coordinate directly here, and your point will actually be processed, or the baselines will actually be corrected. So if I made a mistake with my base station, or if I made an error, so assuming, let's say, this figure was 5, right? I wouldn't need to actually go back to the field. If I correct this value, you could see that the warning is telling me is that the processing software has realized that the setup point has changed. So all these positions, all the positions that were referenced to that particular control point will be affected. So it's going to actually correct all the baselines. So this is how powerful Leica Infinity is in terms of processing RCK data as well. Okay. So it actually saves you time, it saves you money going back to the field to actually process your data. We have a toggle where you can actually check where your points were actually placed on the Google map. So you could see you have a toggle here. So let me just go back to the static data. So if I want to visualize my data on the Google map, if I click on the Google map toggle, I don't know if you can see my Google map. Can you confirm if you can see the Google map?
No.
Okay, let me share the screen. Okay. Okay, let me just, sorry, it's not popping up on your side.
Hello, Derek.
Yep.
Is this the program or the desktop you are sharing? I don't know where you find it.
I think it would be it could be a desktop.
Okay. Okay. I mean your screen.
Okay.
All right.
Okay. Maybe that is fine. So I just wanted to show you how the data it's being displayed on Google Maps. So if you want to visualize your data on the Google Map, then you have this plugin within the software where it takes you directly into the Google Map environment.
So can you see the Google Map on your screen?
Okay.
On
That
yours?
is, yes, I can see on mine, but
so try and minimize this program and let's see if.
Okay.
can hold it and drag it down. Maybe you see, I don't know.
Okay. I think it will be my display. Still struggling to.
Okay, so you go ahead. Maybe later on
Okay.
in our own time you try and see. But if you get a click, then let's know.
Okay, let me. I think yeah. Okay.
Okay, it's here now.
Just confirm if you can see my screen.
Yeah, we can see now.
Okay. So with this plugin, you're able to see the point on a Google map. So this project was actually a stretch in Tema. So you can see clearly from, I think, from the overhead through to heading to Pong Doenya. So you have, you're able to visualize where the points were picked on Google Maps, just to confirm if that is the right positions of where you actually did your survey. Okay. 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 So I think for processing, Gnss processing, Leica Infinity makes it quite simple and easy to use or easy to navigate. So as I said, we have help and support where you can have tutorials. So you wouldn't actually need an expert to actually show you how to use the software. You have tutorials, you have sample data to play around with the data. I think I didn't even mention that Leica Infinity can also be used to process level data. So data from digital levels. So you can actually process data from digital level as okay. So thank you. If there are questions, floor is open.
Hello. I think in Prof's lecture, he was talking about the various corrections and how they were going to be done,
Okay.
especially the time, if we are going to do the correction on the time. So can you take us through those ones?
Okay. So for the a minute, let me. So the orbital or the errors, as Reverend Ayo talked about, so those ones are normally being mitigated by techniques and as well as they've actually built it in the algorithm of the software. Okay, so for example, if you are talking about the tropospheric and ionospheric models, right? So the software normally uses the optimum, which is the automatic. So it automatically selects which model at which point that you were doing your survey. But if you know the specific position and at the specific position and the model at which you are currently you can actually choose which model you want to use for your correction of the either the tropospheric or ionospheric. But these processing strategies are normally built in the software, so automatically it uses the position of where you place your rover and automatically assign a specific model which suits that particular position. I don't know if I've answered your question.
Yes, my question is
Yeah.
answered.
Yeah.
The floor is open for questions. So if you have a question, you may put up your hand, or you can also type it in the chat. What's the name? Derek.
Yep.
Yes. Can you look at the statistics again, and
Okay.
can you relate them, especially the standard deviation and the RMSs? Can
Okay.
you relate them to what it means to the quality of the coordinates that is processed?
Okay. So I'll quickly open the report. Okay. Okay. So you could see from here, this this is the baseline quality for each of the setup. So you could see the point row in terms of the latitude, the longitude, and elevation. Right. So if I come down to where I have the baseline vectors and quality, you could see at each point of the processing where it's getting the data from the base to the rover, you could see I have a change in latitude, change in longitude, as well as change in height. Okay, so these ones are just the difference between the change in X of the reference and the rover. And if I come to the next tab, which is the one on my right, this one more speaks to the standard deviations. Okay, so you could see from the standard deviation for this particular baseline, in terms of the latitude, longitude, and height, you could see the quality here. And if you look at the CQ 1D, 2D, and 3D, so these ones are respect to each of the coordinates. So 1D is looking at just either the X, the Y, or the Z. 2D is looking at X and Y, and the 3D is a combination of the three. Okay. So in order to assess if our baseline or if our processing was successful or not successful, we actually analyze the baseline quality. So in terms of the standard deviation, as well as the position quality here. Okay, and you could see from here that if it's not processed, you have a phase, either a phase float, or code, right? But from this processing, since we have very good standard deviation in terms of the position quality, you could see the solution is phase fixed. So these are the things that we normally look out for when we want to check the quality of the data that we've processed. We look at the standard deviation between the reference and the rover, right? So this is in terms of the baseline. And in terms of the position as well, we look at the CQ, which is, so the 1D is either the eastings, northings, or elevation. So depending on which one we are interested in, because some processing wouldn't actually need or have a need for the height. So we will be much concentrated in the 2DQ, which is the X and Y. But if you are interested in the elevation, then we look at the 3D quality for the position.
Okay, thank you so much. There are some other questions.
Okay, so
It's a follow-up question. With this report, I think because the interface is a bit new to me, can you specify if the various points are listed there and the various standard deviations and the rest? Because I cannot, you were showing change in latitude, change in longitude, but for the various points, can you specify the various errors and those that have been shown in the processing?
Okay, so so you could see from here, this is showing the baseline from the base to rover point 1. Okay, it shows us the reference information as well as the rover information. Okay, so when you come down to the coordinates, okay, you have the reference coordinates and the rover coordinates. Okay, so these ones are the WGS84 coordinates as shown here. And this is for the rover as well. So you could see from the title here, this is the rover data. And sorry, this is for the reference data. This is the rover data. And if you drill down to your right, or if you move to your right, you could see the local coordinates, which we inputted. So the one we inputted for the base is this one. And the one we inputted for, or the one that was processed for the rover is this one, right? So if you come down to what we're seeing during the processing, so if I minimize this page, okay, and I select the first rover point, okay, you could see on my right tab where I have the property tab, you could see I have my baseline quality. And you could specify the type, either you're using the standard deviation or the square factors, right? So normally standard deviation is what we use. So in terms of the standard deviation of error in the X, this is how much error we are getting for the X, how much error we are getting for the Y, and how much error we are getting for the Z, right? So that is the same thing showing in the reporting, but the reporting, this detailed reporting drills down to the latitude and longitude as well as even the baseline, which is the slope distance between the reference and the rover point.
I'm submitting this to SMD.
Okay.
Show all the points, but what you are showing is showing just the base and one rover point. That is what I want to see. That if I have finished my work and I want to print out the reports.
Reports, okay. Yes, so we have the simplified report where you have, so you could see if I go to the home, I have the point code, point quality, and point history. Okay, so if I go to the point quality point, I will have my point, the point row, as well as the eastern, northern, photometric height, and the ellipsoidal height, and the 3D quality, as I mentioned in the detailed report. So the one I was showing was actually a detailed report showing you a bit of the error of the baseline, the satellite that it tracked, the DOP, and so all those information you get it in detailed report. But if you want a simplified report, then yes, you can get it from the point quality report, which is located at the reporting tab. So what I was showing was a bit in terms of having a detailed report of the processing that you've done.
Okay, so Derek, there are a few questions in the chat box. The first one is how can one get the setup of this software, please? The next one says, what is the difference between the TopCon software and Leica software? Well, since you are in the industry, maybe you'll be able to answer. We are drifting you away, but the third one, can we get reference data from another software with the same data and parameters? Next one, or you like to take the three first?
No, you can go ahead.
Okay. Thank you for the presentation. Can you please cite examples where the base can be edited and it is editable in static mode or RTK mode? And is it editable in static mode or RTK mode? Can I go ahead?
Go ahead.
Okay. Is it a proprietary software that takes only data from the manufacturer's GNSS rovers? And then, can the white spaces be corrected from the software environment, or those spaces has to do with the data collected? Thank you.
Okay, so I'll start from the bottom. Okay, so can the white spaces be corrected from the software environment, or those spaces has to do with the data collection? Okay, so those spaces, it has to do with the data collection. So in order to correct them, we actually remove those satellites which had those gaps. Okay, so that's the only way to correct it in the Leica Infinity, just to exclude them in your processing, because those ones happened in the field. So there's no way to actually correct that particular gaps in the data. The only way is to exclude them so that it doesn't affect your the quality of your processing. The one after that is it a proprietary software that takes all the data from the manufacturing GNSS? No. So this processing software actually takes the RINEX format as well. So if you have your data in the RINEX format, so data from the RINEX environment, you can actually bring them in here. Okay. Okay, so can you please cite example where the base can be edited, and is it editable in static mode or rover mode? Okay, so as I said, if you are processing your data, we normally set a point on a reference. Okay, so that reference is actually our control point, which then what the GPX gives you is actually a navigated point. So in order to specify that that is the true point, we can now edit and put in the correct coordinates. So so you could see that for the navigated point, it's impossible for me to edit any of the controls, because any of the coordinates, because that is a navigated point. Those points, I don't know the coordinates, but the ones that I know the coordinates, right, it gives me the chance to edit by specifying that this is actually a control. So if you look at the point rule here, my reference is actually a control. That is why I'm able to edit. Okay. So in rover mode also, you have the chance to actually also edit the base point, not the rover point, because your corrections were actually coming from the base, right? So you could see from here, I have the chance to edit, but if I move to the rover point, I can't actually edit any of the coordinates. Okay. So the next question is, can we get a reference data from another software with the same data and parameters? Yes, so you can actually bring any reference data from any of the software, but if you are importing into Leica Infinity, it has to be in the Gnss data format. Please, what's the difference between the TopCon software and the Leica software? So using me as an example, I've not used the TopCon software before, so I can't really differentiate between how the two software perform. Okay, so please, how can I get the software? How can I get a setup of the software, please? Okay, so with the software, you can get it at our website. So if you go to our website and you just search Leica Infinity, you can get a 30-day trial license, which you can actually install on your laptop and try. But if you are really interested in the software, then you can reach out to us and we can get you a quotation where you can actually purchase the software yourself. We have two types of the in terms of getting the software, we have two various ways. Either you are getting the subscription or the permanent license. So if you get to use the 30-day trial license and you're interested, then you can just reach out to us, and then we can assist you with how the purchase process can be. I think that is the last question in the chat.
Okay.
So the next question is that we've seen that with the RTK, you were able to do some changes in the base. You said
Yes.
if there's an error, how
Yep.
were you able to get the data in the interface here?
Okay, so so this data is actually from one of our GNSS receivers. Okay, so if click on, okay, so this this bit of processing is actually from one of our GNSS receivers, which is the Leica GS18. So data comes in as a DBX file, which I'm not too sure if the other brands have that particular file format. But in order to be able to actually use this this function, then you would have to have let me say a Leica software in order to use this particular function, because the data that comes in is actually a DBX folder. So if you can get that particular file format with the other brands, then you can actually as well import the data here and work with the data in Leica Infinity.
Okay, thank you very much. A follow-up question. You know, normally with RTK, you get a coordinate right from probably maybe the loggers in exporting it or whatever. So yeah, so how were you able to get a raw data with regards to the RTK? Thank you.
Okay, so the raw data, as I said, is the format is the DBX, which we export from our controller. So, you know, normally for the RTK, if you're exporting the data, you're exporting it as a CSV file. Okay, but Leica itself stores so Leica itself stores more information within that DBX folder where you can actually import it in the Leica Infinity.
Yes, Derek. So my question is, this format, the DBS format, can it in any way be edited? By whoever is using it?
In Leica Infinity? No, so that file can't be edited.
Okay.
Yeah. Look for. Then. Okay. I was trying to look for the DBX file. So it's something that it can be edited. So the only way you can actually work or edit the data is when you import in Leica Infinity.
No, you know, the reason why this question came is that some experience is that some people submit data and they try to tamper with the data to suit what they want. Yeah, so I'm looking at it in this form, that in case there is a directive for RTK to be accepted for, say, cadastral work.
Okay.
I mean, in what format can it be received that nobody can tamper with it, but it will go in the raw state that it came. So that it may not be, because earlier when I saw you say you can edit the reference at least.
So that will be a bit difficult if the person owns a Leica Infinity, because he can easily, so assuming if he presents the data and there were supposed to be some corrections, he can easily sit in the house and just edit the reference data, and all the other points will be corrected. So in terms of it being in a specific format, that will be a bit difficult, because you can't have a specific data format where the data is actually protected.
Okay, thank you. I see a hand up. Oh,
yeah, there's one hand.
Hello, my name is Maxwell. Maxwell Oswanza. I just wanted to, I also work with PDSA. I just wanted to give a contribution on the last question, if Derek, if you don't mind.
Go ahead.
Okay, so I guess the question was whether the data can come in a format that cannot be tampered with. So the nature of the data is just the same as a static data. So remember, when you are doing an RTK, you are getting, as the other questioner asked, you are getting your corrections directly on the field. These are stored separately. But as the GPS is on, you can now tell the GPS to store all the data that is being observed, even when you are moving. So all that file, instead of having just a static, so for instance, if your GPS was on for 2 hours and you moved from one position to the other, or several positions, all that file is stored as one file. And it is very similar, I would say, the same structure as a static file, except that for every time that you observe the point, every second that you observe the point, that file is tagged with that timestamp of the time that you observe the point. So the original file that you have is just the same file, but it is tagged at different points. So you saw that when he did a static processing, a particular file was observing from maybe 10 o'clock to 6 o'clock in the evening. Out of that file, you can then have several points. So those points are now tagged. So maybe at 10:45, 30 seconds, a point was observed using RTK. That file is basically tagged with the timestamp of the observation at the time. So then it will come with the point name, point height, and all those things. So essentially, that original file, which looks so similar to the observation file of the static file, is the one stored. And then the timestamps for the other points are stored on it. So essentially, you are unable to change the original file, just as you would have a static file that you cannot change. I hope it helps. Thanks. And sorry, just another one. You can have that file also transmitted in a way that is usable. So let's say in a Rhinex form that can be used by other software. Just as you can have your static data stored in one proprietary format and then sent into Rhinex for data exchange. Thank you. Bye.
Very well explained. Yes, sir. Hold on. Mr. Cornelius Ahianyo, we saw your hand up. Are you okay?
Sorry, this is Maxwell using Cornelius's computer. We are both here.
Okay.
Thank you.
All right.
Okay, Maxwell, thank you very much for your presentation. Sorry, Derek. With regards to the detailed report, I saw something. I realized that the solely GLONASS and GPS. Is it at the time of observation you didn't have anything like Galileo and others?
Yes, so the GPS I was using was just tracking GPS and GLONASS. That is why you only see those two satellite systems. But if you have the other satellite systems on the GPS and you did your survey, you clearly see it in the data representation in the reporting. So yes, you are right. The GNSS I use only two satellite systems, which is the GPS and the GLONASS, which you can clearly see from here.
Thank you. I see one other question. Yes, that one is taken care of. Yes. So please, is it editing the difference coordinates or raw data? I think he's talking about the RTK that you displayed. But I believe that Maxwell had answered it.
Okay.
Unless you want to deepen it. All right. So any other question from any quarter? Okay. So Derek, I guess you are done.
Yes.
Okay. So may I know if Reverend Professor Jonaya is still here with us, and if he has any conclusion or any remarks for us?
Yes, I'm still here with you.
Thank you.
Yes, I'm still here. Derek, the only thing is I do not know, since you are our Ghana reps, do you have our Ghana coordinate system also inside your coordinates, or is it, I see Ghana metric grid, and anytime we say Ghana metric grid, indeed we are still talking of Clark 1880. So I don't know, I want to know if you can influence so that our proper Ghana coordinates can also be accounted for in there.
Okay, thank you, Reverend. Okay, so the software actually gives you the chance to add or specify which coordinate system you want to use. So it's not actually limiting you to a specific, let's say the meter grid. So you could see from this GNSS, the GNSS coordinates system manager or the coordinate system manager, you could see I can easily create my own coordinate system. So in terms of if I'm using the war office, okay, so here I can actually specify with transformation, ellipsoid, and a projection. This is just by creating the transformation here. So it's not actually limiting you to a specific transformation. So you can actually input your transformation parameters and save it. You can have your specific ellipsoid that you want to use and save that, as well as the projection. Then you can now have a complete coordinate system where you can save and use. So you could see from the list I have the Ghana National Grid. I have the War Office and the Clark. So you can equally have your own parameters in there and use it for your processing.
Oh, okay. Very well. I see you also have Legon.
Yes.
And that is the same as the one you are calling the Ghana meter grid, basically.
Yes.
So I don't know. I wonder why you have the two all there. It's the same Clark 1880 that they also refer to as Legion Datum.
Okay.
So, Professor, there's a question there for you.
That is what I have answered. I saw it. That's why
okay.
I answered it. Because the question was saying, so the Legion is for war of peace, and the answer is no. The Legion is actually the same as the Ghana meter grid or the Clark 1880 ellipsoid.
Okay. So, Derek, there are a lot of very experienced and people who have been working with this softwares for a very long time. I don't know, your software, I don't know how long it's been around, but what do you think has happened in the last 5 years with the software that is, that you think you should bring to the attention of those who have been using these softwares for a very long time that they don't know about?
Okay, so now they've actually added sorry. Okay. So those that have already used the software before now wouldn't have the laser scanning data option. Okay, so the version I'm using now has the model where you can process a laser scanner data. Okay, so if I go to my point cloud, okay, so point cloud and imaging is where you bring in your laser scanning data. So these are some of the models that have been implemented in the new versions. So if somebody has a previous version of the software, he might not have the imaging option where he's able to actually process scanning data from a laser scanner. Yeah.
Thank you very
But
much, Derek.
sure.
Hello. Yes, thank you, Derek, and Reverend Professor Aye as well. I want to stand on behalf of the chairman. I don't know if our chairman is here with us, of the LSD. I'm not too sure, but I want to stand on behalf of the chairman and the entire LSD to say a very big thank you for taking time off your schedule to be here with us for this all-important event. I think that we have stayed within the time. Though we started about 20 minutes late, we've been able to complete it within the time that we expected, so people can go home, considering the traffic and other things around. So at this point, I would like to invite my senior Blebo to give us a closing prayer so we can take our leave. Thank you.
Thank you very much, CPD Chair. Let's pray. Everlasting Father, we are thankful to you once again for how far you brought us. Thank you for the education received, and we pray committing all the issues shared with us into your care, that you grant us good memory to be able to practice them and to put them into practice so that our profession will go a long way to build the nation as we all desire. We thank you for the life of the speakers. And we ask that you will continue to abide and protect us in Jesus' mighty name. Amen.
Thank you, Bless. So I want to acknowledge our sponsors once more. And we have PDS, which is part of Hexagon. We also have 360 Survey and Engineering. We have SafeCon Consult, and then Duvergio, which they have been kind enough to sponsor it. So our next CPD is coming on next month, July, and that one we'll be looking for. Yeah, July, sorry. Yes, it's supposed to be in July. So our next CPD will come this July. This one should have been in June, but unfortunately we delayed. So the next CPD, watch out on the platforms for the announcements. And then let's also take note that our conference, that's a seminar as we usually call it. LSD seminar is coming off in Koforidia and is scheduled for 21st to 23rd of August. And so let us all get prepared and then join in the fun. So I will take this opportunity to again appeal to these firms and individuals to come to our aid by sponsoring us to get this event also through. Thank you very much, and thank you all for saving some time for this program. Thank you.